Okay. Okay, very good. So yeah, the outline of the talk is, as I said, I will first introduce this class of groups, topological full groups. You could also say these are groups of dynamical origin, because underlying there's some sort of dynamical system from which you construct these groups. So I will spend some time explaining this construction. And then the main topic of the talk, as I said, will be about homology, how to compute homology for this class of groups. And yeah, I'll present the main results about that. And then towards the end, depending on how much time is left, I will try to explain some of the key ideas that go into this these main ideas. And yeah, really for me, it's an excuse to talk about more results that sort of are useful in understanding homology. Okay, so that's a rough outline, and yeah, feel free to let me know if you have questions along the way. So yeah, so let's talk about these groups of dynamic origin. And really what I like to do first is to explain what I mean by topological dynamics. So this could mean various things to various people. And I want to sort of take the view that topological dynamics are given by certain class of groupoids for me. So this will be my point of view. So let me introduce these a bit and explain what they have to do with dynamics. So first of all, just the definition. So groupoid is just a small category where all morphisms are invertible. That's one way to introduce groupoids. So if you have a groupoid, say G, then you view every element as an arrow pointing from an object called the source to an object called the range, denoted by S and R. And yeah, we, as usual, we view objects embedded into the morphisms. So by identifying objects with identity morphisms, so we just have one set G given by the morphisms. That will be our groupoid. And yeah, so then there's quite a bit of structure that comes with such a groupoid. So first of all, because morphisms are invertible, you have this inversion map sending an arrow to its inverse. Then, I mean, if you think about pictures of arrows, then this is just reversing the arrow. And also you can compose arrows, compose morphisms. So you have a multiplication. In terms of arrows, it's just concatenating arrows. And yeah, so indeed, I mean, another way to think about groupoids is that you could say these are like groups algebraically, but you cannot multiply any two elements. You have to have the condition that the range and source have to match up to be able to multiply them. So that's another way to say that. Okay, and now we want to move on. So this was sort of algebraically what a groupoid is, but now we are interested in topological dynamics. So we add some topology. So first thing we ask for is that the set G has not only set, but has a topology, so it's a topological space. And then immediately what you do is to require that all the structure maps, the range, the source, the inversion map, and the multiplication, that these are all continuous for the topology you have on G. And then there's something more. So there is this, what I call G0. So these are the objects, or as I said, the identity morphisms. So this is a distinguished subset of G. And we want that subset to have a very nice topology, if you look at the subspace topology. So we usually want that to be locally compact in Hausdorff. So I guess you already see sort of my C-star algebra background. So this, for instance, ensures that you get nice C-star algebras, but it's also a reasonable condition to put on the topology. Yeah, it's maybe good to point out that we do not assume that the groupoid itself is Hausdorff. So this might seem a bit strange, but this is to make sure that we cover all interesting examples, because there are some examples coming, for instance, from foliations actually, which are non-Hausdorff as a whole groupoid. Okay. So this is what we would call a topological groupoid. And now let me show you some examples. So I guess the first example is maybe what some might consider classical topological dynamical systems. So you just take a group gamma acting on a space X by homomorphisms. So really just a group homomorphism from gamma to homomorphisms of X. And whenever you have such an action, you can construct what's called the transformation groupoid. So as a set, it's just given by the pairs, one group element in gamma, one element in the space X. And how to view this as a small category? Well, you think of a pair as being an arrow pointing from this point X to gamma dot X, which is the action of gamma on X. So this is where X is sent to under the action of gamma. Right, and yeah, and then, so X has a topology, and say gamma, if gamma has a topology as well, then this gets a nice topology. You just take the product topology, and so you can check then that this makes this transformation groupoid a topological groupoid in our sense, where X is, so this X is identified with the pairs where you take the identity for the groupoid and something in the space component. So X will be our G0 here. And you would want that to be locally compact in Hausdorff. Okay, so that's one example. And I would like also to mention another example. So to be concrete, I want to consider a very concrete transformation, which is the one-sided shift. So the space on React is just a space of infinite sequences, 0-1 sequences, say one-sided. And then you have the shift map, which just forgets the very first or 0th component of the infinite sequence. So this is, again, something that people consider in dynamics. But in contrast to the previous example, this is now not invertible anymore. So this is only one-sided. We'll forget information. But there's a way to construct groupoids also for these type of dynamics. And so what you do is you construct this groupoid. Okay, so what are we doing? So we take the elements in the groupoids are triples, where X and Y are infinite paths in my space. And then there is an integer in the middle. And the requirement is that you can write this integer as a difference of two natural numbers, actually, with the property that if you shift your first point X by K and the second point by L, then you get the same infinite sequence. And so the idea is that this groupoid captures what's called a shift equivalence of infinite paths, that up to finite shifts, you actually look at the same path. And yeah, so this is how you define the groupoid as a set, and then you again, how to view this as a category. You view this triple as an arrow pointing from X to Y. Yeah, so the unit space would be given by the infinite path space, and you connect objects in this way. Okay. So yeah, so these are, I think, for the purpose of this talk, the two classes of examples to keep in mind. And yeah, I think if you look at these, in some sense, in both of them, the groupoids describe somehow the orbits of your dynamical system. So for the first example, this is sort of clear by definition, because orbits are precisely, I mean, the orbit of X is precisely the set of points of the form gamma dot X. But also in this example, you were looking at the orbits sort of for the shift equivalence. So all infinite paths that are shift equivalent to another will be connected by an arrow. And that's sort of somehow the idea that groupoids are convenient notion to describe orbits. Okay, so we've seen now that various sort of dynamics give rise to groupoids, but really I would like to take the viewpoint that even general groupoids you can understand as some sort of dynamics. And to explain that more, we introduce a few more conditions on the groupoids. So we will look at what's called étale groupoids. So these are groupoids which have a basis for the topology of particular subsets, which are called bisections. So a subset of a groupoid is called a bisection if you have this. So sigma is a subset of G, and then we require that both the source and the range are homomorphisms on sigma when restricted to sigma. So in other words, arrows are already determined by what the source is or determined by what their range is. So we want to have a basis of such bisections which are at the same time open subsets. So that's the notion of open bisections. And what I want to say is that if you have a rich supply of these bisections, then you are in some sense looking at some topological dynamical system. And the reason is, if you look at this diagram, so if S and R are homomorphisms, then you can look at the source of sigma, which will be an open subspace of the unit space. You can invert S and then go with R, and that will give you a homomorphism between the source of sigma and the range of sigma. So you get a homomorphism between two open subspaces of the unit space. And so you get a partial homomorphism, and this is somehow the start of having a dynamical system, because if you look at all bisections, these will give you a system of these partial homomorphisms, which you can compose, you can multiply them, and you can invert them. And so you get what's called an inverse semigroup. And this you can think of as a generalized dynamical system, an inverse semigroup of partial homomorphisms on a given topological space. So from the abstract data of a topological groupoid, which is étale, you always produce this inverse semigroup, the system of partial homomorphisms, and in some sense it determines the groupoid in many cases. Okay, and then last thing I need to be able to use these topological full groups is a further strengthening of this condition. So instead of asking for a basis of open bisections, we are actually asking for a basis of compact open bisections. And then the groupoid is called ample. So this has further consequences. For instance, it implies that the unit space in our case will be actually zero-dimensional, so totally disconnected, because they have many compact open subspaces. And the reason we're doing that is because, well, you will see, so roughly speaking, for the topological full group, we will look at these partial homomorphisms, which are only defined locally, and then we then glue them together to a global homomorphism. And this gluing process might have some topological obstructions, but if you have totally disconnected spaces, then these obstructions disappear. This is roughly the idea. So this condition ensures that the topological full groups we'll consider are really rich, that you have many elements, because otherwise they might have very few elements or might even be trivial. Okay, so now the definition. So you take one of these groupoids, these ample groupoids, you have lots of compact open bisections. And then the topological full group is defined to be the group of global bisections. So you look at compact open bisections, as in this picture, but you require that both the source and the range are equal to the whole unit space, so are as big as they can be. Yes, and then
question.
Yes.
So sigma is compact and open in G.
Yes.
Okay.
Yes, as a subspace of G. Yes. Yes. So that's the definitions. You look at these global bisections. and there's a way to multiply two such global bisections because you use the multiplication in the groupoid. So these are subspaces of the groupoid, and you just pointwise form the product, and you check that this gives you another global bisection. So in this way, this becomes a group, and that's what we call the topological full group. As this picture shows, if you have a global bisection, then you get actually a homomorphism of the unit space. Homomorphism from the source to the range, but they are all equal to the unit space. And so sometimes it's people also think about the topological full group as being a subgroup of the homomorphisms of the unit space. Yes. Okay, so yeah, I guess there's one sort of subtle point here where you might want to complain about this definition, because you see the way I defined it, I mean, because I want sigma to be compact. And so if that's the case, then this condition enforces that the unit space has to be compact as well, because it's an image of a compact space. So really this definition only makes sense if the unit space is compact. And there is a more general definition, which avoids this restriction. And so really what you do in general is you take an inductive limit of certain groups. And more precisely, what you do is you run through all compact open subspaces of your unit space. And for each of them, you form what's called the restriction groupoid. So you just look at the subgroupoid subset of arrows where both the source and range lie in your compact set U. Now, this enforces this new groupoid, this restriction, to have compact unit space. It will be given by U. And then you apply the construction to this restricted groupoid. And you do it for each compact subspace. And finally, I mean, this gives you a system of groups, and then you have to find a way to connect them to be able to form the limit. And then what you do is, so if you have a smaller subset inside a bigger one, then there's a way to embed the group of the smaller into the bigger. Because if you have sigma with range and source equal to U, and you want to get to V, what you do is you just add the complement of U inside V to be able to get a bigger bisection. So this is a system of canonical, embeddings, and you form the inductive limit to form the general full group. Okay, so that was the definition. Now let me show you some examples. So first example is when we look back at these classical actions of groups and spaces. And let's even be more precise and just look at integer actions. So integer actions are really just because the integers are generated by one element. So it's really just picking a homomorphism of your space. So you have a generator for such an action. And we assume that X is a Cantor space to have a nice totally disconnected space. And if you have that, and you form this transformation groupoid and look at the full group, and then really what you're looking at homomorphisms of the Cantor space, which locally coincide with the power of this generator, this homomorphism you've chosen. So this really are the elements in the full group in that case. So I have another condition here, minimal. Minimal just means that all orbits are dense. And I put this condition there to be able to state a theorem about full groups. And that's a theorem proved by Monod roughly 10 years ago. interested in these kind of groups, analytic property, let's say, or in various areas in group theory and operator algebras. It has all sorts of characterizations. So, for instance, you could say that if you have a system of Foner sets, so subsets which are approximately invariant under the left translation action of the group, say, or in terms of dynamics, a group is amenable if whenever it acts on a compact space, you can find an invariant probability measure. So it's an important notion, and the interest behind this result was that this led to the first examples of finitely generated but infinite simple groups which have this property of amenability. So that was somehow, an outstanding open question whether such groups exist with this combination of properties, infinite simple or finitely generated, but amenable. And Yushchenko and Monod were the first to construct these examples. Then more recently, Nikolashevich was able to produce a stronger result even. So he found, using a similar construction, looking at slightly more complicated groups acting on the Cantor space, and then constructing the full groups, he found the first examples of such groups finitely generated infinite simple, which have intermediate growth. And so growth is a geometric property for groups. You look at Cayley graphs and look at how boards grow, how the size of boards grows. And intermediate growth, I mean, the most common types of growth, say, are polynomial growth or exponential growth. Intermediate growth is something strictly in between. And again, that was an open question whether you can find infinite simple groups with this type of growth. And Nikolashevich was able to solve that using topological full groups. So I guess these examples show somehow the spirit. So you have these groups coming from dynamics, from groupoids, and then you can produce groups with prescribed properties by choosing carefully a type of groupoid or dynamical system from which you construct these groups. And moreover, that's somehow a special feature of these groups, that in typical cases, they turn out to be simple. So no non-trivial normal subgroups, which is somehow the new feature there. Okay, and the other example I would like to mention, concrete example, is when you look at this other groupoid we constructed for the one-sided shift, this G2. So 2, by the way, just stands for, just remembers the number of symbols. So we were just looking at 0, 1 as our symbols. You could generalize to n symbols, Gn, and you could even look at subshifts, not the full shift. So there's all sorts of variations. But this classical groupoid G2 for the full shift on 2 symbols, if you look at that groupoid and form the full group in our sense, well, what you get is another group that's sort of famous, has been studied for quite some time, and that's Thompson's group V. So that's a particular group which originally was introduced as a certain group of bijections of the unit interval, which are piecewise affine. So piecewise looks like ax plus b, where the slopes are powers of 2 and the breakpoints are dyadic numbers. So there's a particular way to define this V, but it turns out you can alternatively think of this as a full group of our groupoid. And so one result about V and some of its modification is that Skripowicz and Zaremski, they used V and variations, as I indicated, to find, again, first examples of infinite simple groups with particular properties. And this time they constructed groups with prescribed finiteness properties, but sort of very precise ones. So type Fn-1, but not type Fn. So these are finiteness properties telling you that you can find classifying spaces with compact N skeleton for Fn, and they were able to show or construct simple groups which sit between two such finiteness properties. Okay. Right. So yeah, this was just sort of an introduction to full groups and just a bit of explanation why these have been interesting. And now, for the purpose of this talk, as I said, the main question is, what can we say about group homology of the full group? So yeah, I guess if you see this question, I mean, this is a very basic question. So really, it tells you that we know very little about these full groups in general. I mean, they are somehow still quite mysterious objects. It's easy to write down elements of the full group. So some of them are concretely given, but to really say something about the global structure as a group turns out to be complicated in general. In some sense, related to one reason being that the underlying dynamics can have quite complex behavior. Okay, yeah, so we want to understand this question. One motivation being, of course, that this is an important invariant, so it helps us to, say, tell apart some full groups for classification purposes, for instance. But also we hope that by developing tools to study group homology, we hope to be able to, understand these groups better themselves, get a better understanding for these objects. Okay. So before I come to the results, let me explain or tell you two sort of results about homology of full groups that are motivating, that were sources of motivation for us. So one thing is Matui's work. So he had this insight that he wanted to try to understand the homology of the full group by relating it to the homology of the groupoid. So the underlying object, the groupoid, has a homology defined in a similar way as group homology. And so he wanted to relate these two different homology groups. And he was able to make this precise only in low degree, but he conjectured that there should be an exact sequence of this form. So where you have H1 of the full group, and then it projects onto H1 of the groupoid. So this groupoid homology now, this H1 here. And the kernel should be somehow controlled by H0 of the groupoid, but with Z mod 2 coefficients. Yeah, it's called AH, I think, because, well, H1 of the group is just the biennization of the group. So that's the A, and then H stands for groupoid homology. I think it's quite remarkable how he came up with this conjecture. So I think he was just doing lots of computations and somehow, and then had the insight that there should be this type of relation. And this has been then verified for classes of groupoids, but in general, it's still conjecture. Yeah, maybe let me say just for completeness, I mean, I already said groupoid homology, you can think of this as a generalization of group homology. So if your groupoid were grouped, so if the object is just one singleton, then you would just get group homology. But as for group homology, there are various ways to understand or define groupoid homology. So you can construct it very concretely by looking at certain, write down a certain chain complex called the bar complex, compute homology of that. You can understand it topologically by looking at classifying spaces, computing homology of those. Or you could also look at homological algebra and use Tor functors to understand groupoid homology. So all these are analogous to group homology. So that's one thing I wanted to mention. So this conjectured relation between groupoid homology and homology for full groups. And the second thing to mention is this result, rather recent, by Szymik and Wahl, who show for this particular Thompson's group V, which is, as I said, a full group, a particular topological full group, that this particular group has trivial homology. So it's acyclic. And yeah, that again answered an open question. So Brown, quite some time ago, showed that Thompson's group V is rationally acyclic. But then they were able to show that also integrally you have no non-trivial homology. And that was sort of the second motivation, to try to understand why this group is acyclic. Because this is a particular topological full group. And so, yeah, to give a conceptual explanation for this particular homology computation.
Just a question. So the short exact sequence that you said, is it only for ample groupoids?
Yeah, so I think this one Matui was only looking at ample groupoids, yes.
Is it easy to say what the point of compact open, basis of compact open bisections is?
Yeah, I mean, basically the definition of topological full group. So for instance, I mean, if you have like a groupoid with a connected base space, say, then it could well be that this full group has very few elements.
Space recognition to unlock the device.
Oops, sorry. So it could be that you have very few elements in the full group. I mean, it could in the worst case even be trivial. And the reason is that if you're connected base space, then yeah, you might find very few bisections which are global.
It's not going to be the homeomorphism of the space of objects.
Yes. Yeah, so you might not be able to piece it together to something global. I mean, you always find a local one if you're étale. You have lots of these local things. But to find a global one might be hard.
I see.
Yes. Yeah, it's interesting to think about what to do if you don't have ample groupoid but étale, but that's maybe a different story. Okay. So yeah, so that was sort of the two pieces of motivation we have. And now let me come to the results. So this is in the picture, somehow the strategy to try to understand homology of full groups. And yeah, so the strategy is, so we have these ample groupoids. And as I said, we construct these full groups, topological full groups. And now to understand homology, we go quite a roundabout way. So we start with an ample groupoid and construct, first of all, a small permutative category. So this is another word for strict symmetric monoid category. So it's a category where you have a direct sum operation. And I will say more about this, but you build this category from the bisections. So you've seen bisections are important and they crucially feature to construct this category. Now, once you have this category, you can apply the machinery of algebraic K-theory. So you get an algebraic K-theory spectrum for for each of these categories. So you apply this, get the spectrum, and then furthermore, you can look at the infinite loop space attached to this algebraic K-theory spectrum. So yeah, I guess you guys are topologists, so you're probably more familiar with these objects than I am. But so you look at these objects from topology, and yeah, once you're here at the bottom of infinite loop spaces, of course, then the question is, well, why did we do all this? So how does this help to compute a homology of this topological full group? And so to explain that, let me show you the two results. So first result is, and this is now in general for any ample groupoid, that the groupoid homology, that's what's on the left, can be understood as the reduced homology of this algebraic K-theory spectrum. So this is the first connection in this diagram. That groupoid homology can be interpreted this way. And then a second result is, so this is only under some conditions, which I will explain in a minute. And the result says that the homology, the group homology of the full group, can be identified with the homology of this infinite loop space. Essentially, so I have a 0 here to indicate that I just look at the component of the base point for this infinite loop space. Now, so this is really the way, or the reason we're doing this, going this roundabout way, that here the K-theory describes groupoid homology, and this infinite loop space describes the group homology for the full group. Okay, so let me just go through these conditions we have for this theorem, and then explain a bit more what to do with these results. Okay, so we have an ample groupoid and we want it to be minimal. So minimal already came up, so it means that every orbit is dense. It's a dynamical condition. So orbit here means if you look at, say, an object, then you look at all the arrows that point out of this object, and you collect the ranges. This would be the orbit of an object, and you want that always to be dense. So that's minimality. And then there's comparison, and that is saying this. So roughly speaking, what it says is that invariant measures, they control how you can move open sets around using the dynamics of the groupoid. And more precisely, it's saying that if you have two subspaces, and you know that for any invariant measure, the measure of u is less than the measure of v, then this comparison says that there is an explanation why the measure is smaller. Namely, you can find a bisection which moves the smaller subspace u into the bigger one, v. So that's a condition. So if you have this bisection, then it follows that the measure of u has to be less or equal to the measure of v, because the measures are assumed to be invariant. So it means that the source of sigma and the range of sigma have the same measure. And then, because the range is contained in v, it has to have smaller measure. So it's really the other implication that comparison to, that measures already control this type of behavior. Okay, so yeah, we need these two conditions to get this relation. And now the idea is this. So idea is that we want to understand group homology. And the invariant we know, the invariant that's much more accessible is this groupoid homology. So there are various tools to compute it. There's computations for various example classes. So then what you can do once you have these two results is you can pass to the right, and then you just look at homology groups of certain topological objects, so K-theory spectrum and infinite loop space. And then really the question becomes what you can say about homology of infinite loop spaces if you know homology of the K-theory spectrum. And and this type of question has been studied. Ideally, you would like to have a recipe that somehow has this as an input, homology of K-theory spectrum, and gives you this as an output, which, as far as I understand, is we don't quite have that. I mean, if you know more about that, I'd be happy to know. But even without the concrete recipe, there's quite a few things we can say nonetheless. And I'll show you some consequences of these two results now.
Can I just ask something quickly about
yes.
the result? When you say groupoid homology, do you mean the homology as an abstract groupoid or as a topological groupoid?
So not as an algebraic object, but you take the topology into account. Yes.
Okay.
Because algebraically every groupoid is just a bunch of groups, right? I mean, up to equivalence. You just look at the orbits and the stellar groups, and then it basically algebraically you would get not more than a group homology for certain subgroups. but topologically something more would happen. Yes.
Okay. And then also in the second theorem, the homology of the topological full group, is that as a topological group?
That in that case is usually these are viewed as discrete groups. Yes.
Okay.
So I mean, in particular, say if you have some countability, like second countable, if your group was a second countable, then these groups will be countable. So really, they are discrete objects.
Okay. Thanks.
Yeah. So this is understood as just abstract groups, discrete groups. Yeah. Okay. Very good. So yeah, here are some consequences, things you can say now that you have these results. So we assume these conditions are had so that we're in the setting of both results. And one thing you can deduce is you can deduce these vanishing results. So if the groupoid homology vanishes up to a certain degree, then you can conclude that the same happens for the group homology for the full group. So it vanishes up to that degree too, and then on top degree, the group two homology groups coincide. So this explains one of the results I mentioned earlier, because you can apply this result for k equals infinity. And then it would just say that if groupoid homology vanishes all the time, then your full group will be acyclic. And so in particular, this implies and explains why Thompson's group V is acyclic, because it was known that this groupoid G2 has no homology. So that's, if you want an explanation for that earlier result of Szymik and Wahl. Now, as usual, if you rationalize, things become easier. And if you rationalize, you get sort of the ideal outcome, a recipe for the group homology of the full group in terms of groupoid homology. So more precisely, the formula reads that the rational group homology of the full group is given by this construction. So you look at the odd degree homology of the groupoid from this exterior algebra that depends on this symmetric algebra of the even degree part as graded groups. So this is sort of, yeah, what ideally happens, that you get this precise formula. And last thing is related to this AH conjecture of Matui. So we're able to verify this conjecture for this class of groupoids with these conditions. And moreover, we are able to, yeah, sort of improve it a bit more. So we're able to extend it to the left by these two terms here. So one is the second groupoid homology, and this one is the second group homology of the commutator subgroup of the full group. So they sit in this exact sequence. And yeah, so in particular, I mean, Matui, I mean, he had this map, and at first he thought this might always be injective. So you would really get a short exact sequence with 0 on the left. And then later on, people found counterexamples where this was not injective. And so this gives you an explanation. The abstraction for injectivity lies precisely in this second groupoid homology. Okay. So this gives you some examples of applications of the two results. And yeah, I guess in the remaining time, I can talk a bit about the ideas behind these results. Okay, so maybe most importantly, how do we construct this small permutative category? Because that's somehow the key ingredient in what we do. So the idea of this category is, as I said, if basically we want to build a category out of these bisections. So we want to ideally have a category whose objects are just compact open subspaces of the unit space. And morphisms are given by bisections, which have one subspace as their source and the other subset as their range. So that's the idea. Now, the problem with that is to have a permutative category, you need a way to form direct sums. And what would that mean for these bisections? So there is a particular instance where it's clear what this notion of direct sum should do. And that is if you have two bisections which as subspaces of G are disjoint. And because if they're disjoint, then what you can do is you can just form the disjoint union, said theoretically, and that would give you another bisection. So in other words, you really want to find a way to extend this disjoint union operation in a systematic way to form a permutative category. And the idea to make this happen is that you need to create more space to be able to, given any two bisections, to find disjoint copies of them. And really this idea of creating space by amplifying, this is somehow at the heart of K-theory. So yeah, let me explain. So what you do is, instead of subspaces of the unit space, you create infinite copies of that unit space. So you copy on with natural numbers. And then you look at bisections not inside this groupoid, but bisections in some sense of this bigger space you've created. So basically, I mean, there's a way to form direct products of groupoids. And for the second component, you just take the groupoid G, the given one. And for natural numbers, you just take the groupoid where you connect, where you sort of add an arrow between any two natural numbers. So this is somehow the full equivalence relation, if you like. That's a particular groupoid, not that interesting, but in that case, it's the right thing to do. Yeah, so I mean, so why is this somehow really the idea of K-theory? So I mean, if you, for instance, were to form operator algebras of groupoids, then this crossing with this groupoid R really corresponds to passing two matrices of your operator algebra. So that's really at the heart of K-theory. So that's somehow a natural thing to do. Okay, and then now it becomes the following. So say if you have, for instance, on the level of objects, if you have a finite collection of compact open subspaces, so that would be a compact open subset here. And you have another one. So how do you form the direct sum? Well, what you do is you just write them next to each other. And in other words, I mean, these two families of subspaces might not be disjoint, but what you can do is, because you have created this space, you can just shift the second tuple by m. So you shift it to whatever component of n you need to be able to be disjoint to the first tuple, and then you just take the disjoint union. Yeah, so this is really the idea behind this amplification. You create infinite many copies, and then you can always move bisections around to make them disjoint. Okay, so that's this category of bisections, and you would then also define a similar notion for the morphisms, and then you need a way to for a permutative category to be identifying different morphisms for the order. I mean, if you have different order of ways to form direct sums, but this is all coming from this construction you do here. Okay, so that's the construction of this B, and then and then essentially you apply algebraic K-theory machinery, which I will just go through very quickly. So you have this permutative category, you apply algebraic K-theory to get the spectrum, and so that means you get this sequence of spaces. In our case, X0 would just be a classifying space of B, and then there is a machine that produces all these other spaces with maps between suspensions of Xn and Xn plus 1 to get a spectrum. yeah, in our case, we get this particular property that the n space is up to homotopy the same as the loop space of the n plus first. But this only holds for n bigger or equal to 1. Yeah? So it might or might not be true for n equals 0. So it's this kind of omega spectrum, but only in positive degree. And then the infinite loop space then sort of takes care of this potential problem at n equals 0. So in our case, one way to say it is that it's just the loop space of x1, yeah, which would be x0 if you wanted this relation to hold everywhere. Right, and so that's an infinite loop space because up to homotopy, it's a loop space of a loop space of a loop space, and so on. And yeah, so these are the two objects, this K3 spectrum, this infinite loop space, that have come up. Okay, so yeah, so I have now slides for the two theorems, just quickly explaining the idea. Do you want me to continue until full, or do you want to stop now? Yeah, continue until full, okay. Okay, so yeah, I can quickly say sort of the idea is how to get these main results. So the first main result was identifying groupoid homology and homology of this K3 spectrum. So one way to prove this is the following. So you look at a particular way to understand groupoid homology. And the particular way is sort of, it's like this bar complex, but in space form. So there is a semi-simplicial space you can write down, particular one, and the groupoid X, and you just form equivariant homology of that simplicial space. So that gives you by definition more or less groupoid homology. And now what you do is you do the construction we did and apply it to this semi-simplicial space. So for each of these spaces, you form one of these permutative categories. So somehow you mimic this semi-simplicial space at the level of categories. But what you gain is that, I mean, each of these categories, they're somehow easier to understand because these spaces, the G action on them is what's called free and proper. So yeah, these are nice G spaces because you can form nice quotients. And that somehow makes the analysis of these categories easier. And then very roughly speaking, because you can compute homology for the K theories of those, you can do that and then compare homology of the groupoid and of the K theory spectrum using these sequences. So this is very quickly sort of the idea behind the first result, that you mimic this semi-simplicial space. Okay, and then for the second result, how do you get this connection to infinite loop spaces? This has two ingredients. So one is a well-known one in algebraic K theory, and that's what's called the group completion theorem. First discovered, I think, by McDuff and Siegel. So that applies directly to our result, to our setting. And what it gives is not quite what we want, but close. So it gives you that the homology of the full group, not of the groupoid itself, but of this amplified groupoid, is always the same as the homology of the infinite loop space. So that's what you get from this completion theorem. And then what remains to be done is to get rid of this amplification again. And to do that, what you need is this kind of theorem telling you that group homology for full groups is invariant under what's called equivalence of groupoids. Yeah, so in other words, it says that if you have groupoids and you restrict, in the sense we had earlier, to any compact open subspaces, and then the full groups have the same homology, no matter which subspace you choose. Yeah, so this in particular applies to these two groupoids where you take R cross G and G, because you can get G from R cross G by restricting to a particular subspace. And then this result here would tell you that up to homology, these two agree. And so that's the way you get this result. And maybe one remark is that, I mean, to prove this, that's the point where I need these extra assumptions. This result here is in general. So in other words, the theorems I told you, they have unconditional versions where you don't assume anything. If you are willing to replace full groups of G by full groups of this amplified version of G. So there you get general results. Yeah, okay, I think that's all I wanted to say. Thank you very much.
All right. Are there any questions? I have a couple of questions myself. Could you say a little bit more about these dynamical conditions and how they come into proof? Yeah.
Yes. Yes. So yeah. So there's these three conditions, and so sort of to explain why they are related. That's related to the strategy of proof here. So the strategy of proof is to use what's called homological stability. So that's a framework introduced by, I think, in particular by Wahl and Randall-Williams. So it's a way, because I mean these different groupoids, they form a system. If you have U inside V, then you have embeddings. And this is sort of the setting where you want to observe homological stability, that these systems, they always have the homology stabilizes, or in our case, is actually always the same. And Randall-Williams and Wahl, they have produced a setting where you can check, or criterion you can check to be able to deduce homological stability. And it's to check their conditions, that at the moment these conditions on the groupoids are needed. So that's somehow the reason they're there at the moment.
For example, is it easy to say how having dense orbits is related to their conditions?
Yeah. So I mean, okay. So I mean, in the conditions, they construct certain auxiliary categories, and then you have to prove certain homological vanishing results for these categories they construct. And the idea is, I mean, if you have, say, minimal and comparison, say, then you have a very good control how to move around open subsets in your groupoid. Yeah? Because minimal means you can move one point to any other point. And comparison tells you just need to look at measures, whether you can move it or not. And so this moving around, this is precisely this kind of flexibility you need for the categories they construct. So you can construct categories based on the dynamics, and then you need this flexibility, which is guaranteed by these conditions, essentially.
I see. Maybe another question. Could you say what fails in the tall groupoids?
What fails? What do you mean?
To do the same type of calculation.
Yeah. So I guess the problem is, as we sort of discussed, if you just have an état groupoid without ample, then the full group might see very little of the groupoid.
But there are examples in foliations, the full group is large.
Yes. And then I think at the moment we don't know much about that case, because this sort of homological stability, for instance, really needs this extra flexibility, which you wouldn't have unless you have zero-dimensional base space, I think. So yeah,
I see.
so at that point, at least, that's all I can say about that. But it's definitely interesting to understand better what's happening beyond zero-dimensional case.
Mhm.
So you mentioned the special case corresponding to the result of Szymik and Wahl. So in their case, they proved some kind of homological stability, and then they in fact they deduced that it holds in all degrees because of some kind of self-similarity. Is that the case? Is that how you do it in your setting as well? There's some kind of self-similarity that means that homological stability implies that these are really isomorphisms in all degrees.
Yeah, so I mean, self-similarity, that's a very special thing about Thompson's group V. In our case, yeah, you don't quite have that, but the replacement somehow is, again, as we said, this flexibility you have if you have these dynamical conditions. So basically, I mean, in the groupoid, because of minimality, you have many copies of the same point. So there's some sort of similarity or homogeneity because of these dynamical conditions, and that's somehow good enough to get from stability to isomorphism. Yeah.
Okay, because the output of their machine just gives you something in a certain range. It can't tell you something in all degrees.
Yes, indeed. Yes, indeed. So you need to, I mean, you need to apply that and then do something slightly more to get isomorphism on the nose. And and there you use this dynamical flexibility.
Okay, and this is somehow ensured by one of these conditions, by minimality?
This is actually the combination of all of them, I would say. I mean, yes. So you really need all, and you can actually cook up examples where, say, if you don't have this condition or you don't have minimality, then this would fail.
Okay.
So you would get different homologies. Comparison, maybe I can say, is a mysterious condition, because at the moment we don't have an example of a minimal groupoid which fails comparison. So we can't really say much about that at the moment.
So in particular, there can't be known counterexamples where just that fails.
Yeah, at least we don't know at the moment whether something like that exists. Yeah,
thanks.
Yeah.
I don't know much about Thompson groups, but I know that there are many different variants that people are interested in, like higher dimensional versions, or on the interval, the ones that have different type of slopes, not just powers of 2 and so on, like powers of 3, and somehow they behave differently for them.
Yes.
Is it useful to use this machinery to calculate their homology?
Yeah, so many of these variations, they are also full groups of groupoids. So you play around these groupoids. Say for instance, I had G2, you have Gn. This is one variation, which would correspond to, instead of powers of 2, having powers of n as your slopes, for instance. And so you can apply the same machinery and compute homology as well. But the case of V is special in the sense that you get the final answer because you're lucky that homology vanishes. In general, you might not be able to say to completely compute everything in all degree. So rationally, for instance, you can say that these variations also have vanishing homology, but they might have torsion. And then it's quite tricky to compute all homology groups on the nose.
One thing is, instead of the V version of the Thompson group, you probably know there's F and T version.
Yeah.
And I mean, for myself, the F and T version are more interesting than V, because they come from the homeomorphism of the circle. And for the different versions, like the higher slopes or even higher dimensional, you can still think about the F and T version.
Yes.
And does this machinery tell us anything about the homology of those groups?
Yeah, that's a tricky question. So even for like the classical case, V, F, and T. So for F and T, there's no good way to write them as full groups of a groupoid. So, I mean.
But the group homology is known in those cases.
Yes, yes. But that somehow, yeah, wouldn't go through this this machinery that I've explained. So that would be maybe looking at particular complexes to act on and doing things differently. So I don't know how to use that machinery to say something about F and T.
Yeah, I mean, I have a comment about that, but maybe I should stop and see if anyone else has a question.
Well, I just had I don't know if it's not directly in a slightly different direction, but is there an ample groupoid with these conditions whose topological full group is just the full homeomorphism group of the Cantor set? Can you reprove that the homeomorphism group of the Cantor set is acyclic using this machinery?
That's interesting. Full homeomorphism. Yeah, I don't know how to construct that groupoid, at least for now. I mean, like at the moment. Yeah, I wouldn't know how to construct the groupoid. Yeah, but I mean, yeah, so it would be strange because I guess that's not countable, for instance, right?
No.
So it would, yeah, so if your groupoid is second countable, then the full group would be countable. So it would be a rather strange groupoid. But yeah, I don't know how to construct that groupoid if it exists.
Okay.
Yes.
All right, so maybe I stop recording now.